The speed of sound is about 1,235 kilometers per hour, or 768 miles per hour. And no, I'm not going to delay the audio of the entire video like that. But that is what you would have experienced if you were just 150 meters or 500 feet from this video. Unless, of course, you are in an acoustic shadow zone. But anyway, the reason I say the speed of sound is about 1,235 kilometers per hour is because the speed of sound is not absolute. Partially because sound isn't really a thing. Sound is often compared with light because they are really the two largest building blocks that give us our perception of reality. But unlike light, sound can't exist on its own. Light can travel through space all the way from the sun to Earth without anything there in space, but sound could not. You see, well, light was created as electromagnetic radiation and is therefore propagated by electromagnetic waves. Sound is composed of mechanical waves. Putting that into simpler terms, light is its own thing, electric and magnetic fields that are made of photons. It can therefore travel on its own without anything else around it. But sound is not its own thing. It requires a medium with which to pass through, otherwise it simply doesn't exist. As a mechanical wave, sound requires physical interaction between the medium's molecules or their bonds. The best way to visualize sound is with a grid. The grid is the medium or substance through which the sound is traveling. The points on the grid are the material's molecules. The lines connecting the dots are the bonds connecting the molecules together. In elastic or springy materials, the only materials through which sound can travel, these bonds are compressible. This is what allows sound to propagate, so we'll visualize these lines as springs. For simplicity's sake, we'll only visualize one sound wave at a time, and at a much slower speed. Otherwise, it'd be a confusing mess. There are two types of sound waves, shear waves and compression waves. Shear waves only exist in solids. Liquids and gases don't have shear waves, so for simplicity's sake, we'll focus on compression waves. If a sound is created on this side of the material, the sound propagates through the material like this. The amount the wave compresses and stretches the material is the amplitude or volume of the sound, and the speed of the wave is the speed of sound. This speed varies greatly depending on the material and the material's temperature. This is why there is really no absolute speed of sound. There are a fair number of factors that play into what the speed of sound is for different materials. For solids and liquids, the speed of sound is most affected by the material's stiffness and density. For gases, however, it's primarily the temperature and molecular structure of the gas that determines the speed of sound. Air is basically an ideal gas, so the speed of sound in air is primarily affected by the air's temperature. The colder the temperature, the slower the speed of sound, and the hotter the temperature, the faster the speed of sound. At a typical 20 degrees Celsius, or 68 degrees Fahrenheit, the speed of sound through air is about 1,235 kilometers per hour, or 768 miles per hour, or about 0.0001% the speed of light. A common measurement in various fields, such as aerodynamics and ballistics, is Mach number, named after physicist Ernst Mach, who captured the first photograph of a bow shockwave on an object traveling faster than the speed of sound. Mach number is not a specific speed, but instead the ratio of an object's airspeed to the speed of sound. Mach 1 is always equal to the speed of sound, but of course the speed of sound is not always the same. For example, 100 kilometers per hour could be Mach 0.081 if the temperature is 20 degrees Celsius, or 100 kilometers per hour could be Mach 0.084 if the temperature is 0 degrees Celsius. The fastest manned aircraft ever was the X-15, which traveled at a top speed of 7,274 kilometers per hour, or 4,520 miles per hour, which at an altitude of about 31 kilometers is Mach 6.7, 2 times faster than the renowned SR-71 Blackbird. Because of the incredible speed, the surface temperature of the X-15 on some of these missions reached temperatures of over 700 degrees Celsius or 1,300 degrees Fahrenheit, simply due to friction with the air. The average temperature of Earth's atmosphere varies greatly depending on the altitude. What's interesting about this is that up to about 11 kilometers, the temperature of the air decreases, which causes the speed of sound to decrease as well. This causes an interesting phenomenon where sound is actually refracted upward and thus causes an acoustic shadow some distance from the source of the sound. Wind gradients can also decrease or increase this effect to such an extent that in some cases the sound of war can't even be heard just 3 kilometers away. In fact, on one occasion during World War I, a bombardment of German cannon fire could not be heard 50 to 100 kilometers from the source. The sound was heard past the 100 kilometer radius, but anyone inside the 50 to 100 kilometer radius could not hear the explosions. This means that air temperatures and wind gradients refracted the sound first up, but then down. These temperature and wind gradients are the reason why sometimes you will see a flash of lightning, but never hear it. It's not necessarily because you're too far to hear it, it could just be because you're in an acoustic shadow zone. One advantage sound has over light is that, unlike light, sound can travel through almost anything, so long as there is something. We generally think of sound traveling through air, but sound travels through much more than just air. In fact, the speed of sound is generally faster through solid objects than it is through air. Even though the speed of sound through air is generally a fairly slow 1200 kilometers per hour, the speed of sound in steel is 21,600 kilometers per hour, or 13,422 miles per hour. The speed of sound through water is also faster than through air, at about 5,400 kilometers per hour, or 3,355 miles per hour. Although in steel and water the speed of sound is faster than through air, the speed of sound through rubber is slower than the speed of sound through air at a quite slow 216 kilometers per hour, or 134 miles per hour. Diamond compensates for whatever rubber lacks though. Since diamond is one of the stiffest substances we know of, the speed of sound through diamond is one of the fastest possible under normal circumstances. The speed of sound through diamond is an absolutely mind-boggling 43,200 kilometers per hour, or 26,843 miles per hour. But this absolutely mind-boggling speed is only 0.004% the speed of light.